then. Yeah, okay, this is part 7, I guess, yeah. Right, this bit I haven't explained, and I need to explain it. Well, I have explained some of it in the past videos, but I suppose I need to do it again now. But basically, when I take my magnet gauge out, which is telling me what the flux is doing. But as I was explaining, the reason this works is because of the way my device intercepts flux lines and acts as a firewall, basically. Now, let me get my bias in, and I'm going to take something off and show you what happens. Now, when I move this that way, let's see, that's pulling. Right, when this magnet is pushing, now look at that, it's pushing it, look. Oop, it pushes, right? See that pushing motion? Look at that, right. See how much that's pushing, look? Right, I'm just resting on there. I'm not pushing it though. Right, now, let's put this on here now. Now if I stick my device, the magnet on here, it pulls to that one actually, it's pulling to that one. Right, we're not pushing on this one though, because look, if I push it just past there, it's pulling towards this one, yes, because it works as, it only allows one flux field through, and I want it to accelerate towards the next state anyway, but I just don't want it to have any drag. Now, at the moment, it's not moving, it's only going to get pulled towards the next one. So I've got to keep this sort of in the middle so it doesn't push away. It's not pushing against there right now, okay? Now, if I take this top concentric off, right, including my biasing magnets, now, if I put my biasing magnets on the first concentric, right, not the second one's been removed. Now watch what happens. Now it won't stay there, look. I cannot get it to stay on there. Look, it's right there. Release my hand. It will not stay there. It's now pushing. Okay? So I've got the equal opposite reaction happening now. Right? It's actually now it's pushing on there. Right? So how does this work? Alright, I'm going to explain it. Now, take my magnets off again. Put the concentric arrangement on. There's 2 stages. Put that back on. Now move that back to the middle. Put the magnets back on. It's not pushing anymore. So how does that work? We can get it to pull towards the next stage, but that's okay because remember the equal opposite reaction is pushing against is an opposite reaction. But while this is an opposite reaction here, right? Over here it's an equal reaction, it's a pulling, actually I'm lifting it up now, look. It's pulling. But we're not worried about that. I want to use that to my advantage to accelerate the rotors when they're spinning. Alright, so how does it work? Right. There's a concentric magnet array. Right, I'll just take one of them off so I can show you. That's what it is with a ferrite ring in the middle, and there's actually 12 magnets in there because there's 6 slots, but in each slot there's I think it's 5 millimeters by 3 millimeter thick magnets, and there's a whole bunch of them in there. And the way can't get the words out today. The way they are polarized, we're just referring to the inside polarization when I've color coded them. So it's basically north, south, north, south, north, all the way around. Okay. Now this is a side view. Right. This is the rotor. Right. So this is our rotor magnet. This is what is sending out a strong magnetic field. Now the way that works is it will attract the opposite field towards itself, but it will repel the other field towards the other concentric. So what's happening is the flux. One field is being subtracted towards the field, which is why we have an equal balance between the two. It's actually pushing and pulling at the same time, so it's in a balanced state. No matter how far apart it is, it will stay balanced because it's pushing and pulling equally, no matter how far away or close together it is. So right, while this is subtracting the north or the south field, right, this particular magnet is now being shunted away, so it's actually attracting on the south or the north on this other side here. So this field is being drawn this way. This field is being expelled this way. So we have these, like, these are the basic directions of the flux of these different polarizations. So we've got this flux going, it's acting like a firewall basically. So, and on the opposite side we have our, we actually have the opposite reaction is here, right? This is our coil or simulated opposite reaction force. So what's happening here now? We have the south field or the north field. I get mixed up which is bloody color coded actually, but I think it's north actually. So this is being subtracted. North is being subtracted towards this. South is being subtracted towards the red. Well, let's just say blue. Let's use color codes. Blue is subtracted towards the red, and the red is being expelled because this is also red, and it's being absorbed by the north poles on this side, because these north poles over here, right, are in a state of balance. Volatile flux balance, so they're going that way and they're going that way, so that there's a tug of war going on between the two. So most of the forces and the tug of war is going on between these two concentrics, which are acting like a firewall and isolating the lens effect. So the lens effect is basically trapped in this array here. So when I take one of these off, which is what you saw me do, when I take one of them off, then there's a more direct path through. The red would be subtracting this north, or this blue. Sorry, the red is to subtract these blues, and there's only one barrier between the two, right? So we are able to see the lens effect taking place. But because I've got two barriers, we have basically a magnetic trap. I think that's the best way to explain it. Alright, I hope that explains it. Thank you for watching.